Today we're going to look at something called the binomial distribution. And to start off with, we're going to look at a little demonstration using a tree diagram, kind of look at our probabilities, and then get into some new material. So I'm going to start off with the probability if you were shooting a basketball, trying to get it into the basket. And let's say the probability of doing that, probability of success, was about 75%. So in other words, if you were to shoot 100 baskets in a row, we would expect 75 out of that 100 would be successful. Okay, so let's have a look at, you're going to do 3 tosses in a row. And I'm going to do my little tree diagram here. So on the first toss, I'm just going to say you either get the basket or you miss. And the probability of getting the basket is 0.75 and missing 0.25. So that's our first toss. Then we go to the second toss, which is either going to be a basket or a miss. So 0.75, 0.25 for the miss, and the same thing down here. Now, we are in fact considering these to be independent, and that means that whatever the first toss, whatever the outcome, these probabilities haven't been affected. So I don't know whether that's a totally accurate statement, but for our tree diagram, we're claiming that it is. So 0.75 and 0.25, and I said we're going to try 3, so we have to go one more branch. So a little bit of writing here, but that's going to help us analyze the whole business pretty well. And all of our probabilities here. So basket and a miss, 0.75 and 0.25, basket and a miss. So there's our tree diagram. Now what we're going to do is take all of these branches which outline all conceivable possible combinations of what could happen with your 3 tosses, and we're going to kind of look at them in a slightly different way. And I think what I'm going to do is start my little assembly down here, and the idea here is to say, well, the baskets, and right next to it the probability, and kind of in between I'm going to think of how many branches that includes. So what are the possible things that could happen? Well, out of your 3 tosses you might not score any. Okay, you might miss all of them. Or you might get 1 basket, or 2 baskets, or 3 baskets. So let's have a look now at the corresponding probabilities. No baskets means a miss, followed by a miss, followed by a miss. And so the probability, and that's the only branch, by the way, so the probability is 0.25 cubed. Now, then we look at 1, scoring 1 basket. Now, there's a couple of branches that are going to work for us. In fact, there's actually 3. We could go this branch here, basket, miss, miss. And you'll notice the probability is 0.75 times 0.25 times 0.25. Okay, so I'm just going to make a note of that. That would be 0.25 squared times 0.75. Okay, because we've got the 2 misses and the basket. So there's 1 branch. Then we could have a miss, a basket, and a miss. Even though the order's changed, it's still 0.25 squared times 0.75. So I've got 2 of those. And lastly, I could have a miss and a miss and a basket. So I could have 0.25 times 0.25 times 0.75. So there are 3 of those. So I'm just going to put a 3 out front. Okay, so then we have 2 baskets. Now I see that's kind of do that for clarity. The success of 2 baskets. Well, we could have basket, basket, miss, basket, miss, basket, Okay, and that's 0.75, 0.75, 0.25, and the order changes, but what we see here is that we have a 0.25 and 2 of the 0.75s. Now, I just mentioned basket, basket, miss, basket, miss, basket, so there's 2 branches on the top here. Then we have miss, basket, basket. So again, 3 branches. And finally, at the bottom here, the 3 successes would just be basket, basket, basket. And that would be 0.75 cubed. So, what do we see happening here? 1 of these branches, 3 of these, 3 of these, and 1 of these. So, very interesting what we see with this 1, 3, 3, 1. Some of you might recall that Pascal's triangle had something about 1, 3, 3, and 1. But we'll get into that in a moment. What I'm going to do now is take this data, which we have here in a table, and I'm going to write it up in a slightly different way. And this method is the most common way of seeing what we call a probability distribution. There's that title, distribution, showing up. So let's make a little room here and show you what that might look like. So we'll just get rid of our tree diagram here and show you what this little probability distribution would look like. So I'm just going to hang on to this stuff here down at the bottom. Okay, and what we would have happening would look something like this. We'd have our probability as the y values, and all these different types of combinations of outcomes along the x-axis. So this would be number of successes, and this would be their corresponding probabilities. And so we would have possibly no baskets, 1 basket, 2 basket, or 3. And the way we like to look at these is the form of a histogram. And so if I work out what these probabilities are, and I've done that ahead of time, you can do that as well if you wanted. This one here turns out to be about 0.016. The next one is 0.141. And this one here, if we multiplied all that, would be 0.422. And then the last one would be 0.422. And so what this gives us is actual numbers, and the probabilities here go up to about a 0.42, up to about a 0.5 is what I'm going to make the top, so 0.1, 2, 3, 4. Okay, so there we go. And now we can just approximate these and build up our histogram with these probabilities. So we get kind of a nice little graphical kind of display. So 0.016, that's pretty small. Might be something like that. And then the next one's 0.141. It's a little bit higher than the 0.1. So about like that. And then we have 0.422 and another 0.422. So that's about up to about here. And I'll just take that right across. And that's what this particular probability distribution would look like. Now keep in mind, this probability distribution has this kind of a look, largely in part because the probability of success, of any one success, was 0.75. And if we had changed that probability of success and we had worked out all these different branches, of course we'd have different probabilities and a different look to that histogram. Okay, let me just show you something else here. I mentioned Pascal's triangle showing up here, and that's very true. And I also have here kind of these little probabilities. This one's cubed, then squared, then to the 1, and then it disappears. and kind of this one happening in reverse order. So let me just show you a way of visualizing this. Suppose I thought of this as 0.75, probability of success, plus 0.25, and I cubed it. Okay, now why cube it? Well, maybe because we took 3 possible shots at the basket. So that's kind of why that 3 happens there, and maybe that's coincidence, maybe not. But if I use the binomial expansion on this, what would it look like? Well, my first coefficient here would be 3, choose 0, which happens to be a 1, just like that number there. And then I would have in here 0.75, and that would be cubed, and I wouldn't have a 0.25. Now you'll notice that's actually this last term. It doesn't really matter whether the order is different from the way I wrote it here. In any case, I think we're going to get all these same combinations. Plus. If I continued on my expansion, I'd have 3, choose 1, which happens to be a 3. And then we'd have 0.75 squared times 0.25. Well, that looks an awful lot like this term right here. We got our 3, we got our 0.75 squared, and we got our 0.25. Well, if I kept going, the next one would be 3, choose 2, and we'd have 0.75 to the 1 and 0.25 squared, which of course turns out to be the next one here. And then the last one would be 3, choose 3, which is a 1. 0.75 drops off, and we've got our 0.25 cubed. Well, what we see here is if we think of these probabilities and we raise it to an exponent, and that exponent is the same thing as the number of times that, number of trials, I guess would be a way to describe it, that it expands out and gives us exactly the probabilities that we had from our tree diagram. Well, this is a great observation because we can avoid the tree diagram. I mean, that was a lot of work. You got to draw your little branches and little probabilities, and it gets pretty messy. So now I'm going to just summarize it. We don't ever need tree diagrams and all that messy stuff necessarily again. Of course, they're still good in their own little ways, but they're nice to avoid as well, I suppose. What it kind of boils down to, we make a few little observations here, is we had 3 throws, and where did that 3 come in? Well, we had 3, choose 0, 3, choose 1 as our coefficients. So I'm going to start building a sort of a general form here, and look at it this way. Then what we had was 3, choose, and now I got to decide, since this was a changing number, 0, 1, 2, and 3, what are we going to call that? What exactly was the 0, the 1, 2, and the 3? What did they represent? They actually represent the number of successes. Remember that we had this term here represented, in this case it was 3 successes, and then we had this one down here representing 3 failures. Now the interesting thing is that this coefficient is the same as this one. So rather than to do a more complicated formula, what we end up doing is we say it's easier to think of this one and just say 3 successes, even though technically 3 successes was this one up here. I guess maybe that's not all too clear. Let me summarize that first in a slightly different way, and then we'll generalize the formula. Okay. Those 3 throws, we're going to say, okay, let's generalize with n. So the 3 throws we're going to call n trials. And so that is an easy one. That would just be n choose and then we'll fix that other number in a moment. So n choose, and we'll fix that up in a moment. Then what did we do? Whoops, got my equals. Jumped the gun there. Then what did we do? We said, well, let's take the probability of success, like the 0.75, and what we want to do is, well, sometimes it's cubed, and sometimes it's squared, and sometimes it's to the 1. Now, this one's pretty clear, easy to work. When it was cubed, that meant it was 3 baskets. When it was squared, then it was 2 baskets and 1 miss. When it was to the 1, it was 1 basket, 2 misses. So what we want is this number here to be the number of successes. So I'm just going to call that x. Okay, and then I'm going to get back to this guy down here. Okay, so x is the number of successes. So n trials, x successes. Okay. And then what do we have? Well, we have the probability of failure is right next to it. That's this 0.25. So I'm going to call that q. Okay, so q is the probability of failure. And then what's this exponent? Well, notice that these two exponents here, the 2, and then there's like a 1 there, and then there's a 1 and a 2, and then there's a 3. They always add up to whatever n is. So what we do is we just say, well, take n minus x. Okay? And that's going to give you the correct exponent here for your probability of failure. Now the other thing is to go back to this. Now technically speaking, what number we want in here is technically n minus x that you could put down here. If you think about it, for example, if you had, well, let's start with 3 successes. 3 successes, so we kind of would want a 0 down there. So we would go 3 minus 3. If we wanted 2 successes, we'd kind of want a 1 down there, so we'd kind of go 3 minus 2. But since this coefficient is the same as this coefficient, and the second coefficient is the same as the second last coefficient, it's easier to just say, put an x in here. Okay. In other words, 3 choose 3 is the same as 3 choose 0. Sorry, I was pointing at the wrong thing. 3 choose 3 is the same thing as 3 choose 0. And that way, there's a little bit less clutter in our formula. It amounts to the same coefficients that we would get if we visualize this as n minus x. But it's just a little bit simpler. So again, let me just summarize the parts of this very important formula. Okay. And we'll get rid of this guy here. I don't think we'll need that anymore. Pretty messy looking stuff. What we have is, well, n trials, x successes, and here we have p represents the probability of success, q represents the probability of failure, and 3 throws. In this case, well, I'll get rid of that because that was specific to our example. What we have is n trials, or n throws, and x successes, and so this gives us the probability of what? Well, probability of x successes. And so that's what all this, really this guy down here in particular, gives us. So that's a pretty handy little formula. We can kind of bypass a lot of trouble with the tree diagram and counting branches by working with this formula. And it's a pretty easy one to use. The other thing that I haven't really talked about is this whole business of binomial and what exactly a binomial distribution is based on. It's what we call a binomial experiment. And a binomial experiment is one that has only 2 possible outcomes. Well, it's not exactly true. It can have more outcomes, but we consider one or more of those outcomes to be successes. And whatever we group as the rest of them, we consider failures. An example of that might be if you roll a die, you might consider rolling a 1 and a 2 your successes. So the probability of success would be 2 out of 6 or 1/3, and all the rest of them are a failure. Okay, so it's not as if you have, well, this is a success and this is kind of not quite as much success, and then we got a bit of a failure and then a really big failure. That's not binomial. Binomial has only success and failure. Okay, so that's the idea of the binomial experiment. Well, let's keep this guy handy and work through an example or two, see if we can figure this stuff out, make some sense of it. Okay, so we don't need that. We'll get rid of that as well. Just keep our formula handy. Alrighty, so my first example here, we're going to go to basketball again, and somebody said, well, the probability of let's see, scoring a basket, I guess, is 0.85. So this guy's just that little bit better. And so we're going to look at, well, what's the probability that he scores exactly, let's see, make sure let's see, 13 out of 15 shots. Okay, so here's our basketball guy. He's going to take 15 shots. You can imagine the tree diagram would be enormous. So that's why this is a way better way to go. He's going to take 15 shots in a row, and we want to know the probability he's going to score exactly 13 out of the 15 shots. Okay, well, according to this, n here is the number of shots, so we would go 15, choose, and x here is how many of those we consider success. Well, 13 successes, so that's our coefficient. Then we have p, the probability of success, is 0.85. So when you think about it, it's like if you think of one branch on your tree diagram, okay, you're going to have 13 of these 0.85s, right? Because you want 13 successes. So there's going to be 0.85 to 0.85 to 0.85. And then you're going to have how many failures? Well, 0.15, because they got to add up to 1. And we want 2 failures. Okay? So you think of your number of trials, 13 and 2, and 13 successes, 2 failures. There's your coefficient. That's how many branches. Okay, if we counted up all the branches, this is how many branches there are altogether. Now you just throw it in your calculator, and you got your probability. I did that. I worked it out, and I got 0.28, and we'll just go round it to 3 decimal places. So 0.286. So that is a very fast way to do it. Well, so you're thinking that's pretty good. Let me show you an even faster way that's built in most calculators. We could use the formula, or we can go to our calculator, and I can only speak for the Texas Instruments type of calculator, but here's where you would go. You would press the second function button and choose vars. And under that, or actually it's the, you'd see there's kind of the little word distribution is the one that we're actually accessing. So we go into distribution, and then you choose binomial. So here's the one you choose, binomial, and PDF. Now PDF stands for probability density function, and all you have to do is visualize that this little PDF has a very big importance between, there's another one that says binom CDF, cumulative, and we'll talk about that one in a moment. Let me just show you what PDF actually means. If you visualize the histogram for this particular distribution, it would look something like this. You would have, oh, he's missed all 15, oh, he scored 1, oh, he scored 2 out of the 15, all the way up to he scored 15 out of the 15. So I'm just going to back it up a little bit, and here we got number 13. And along this side, of course, we got our probabilities, right? what we want, the probability of getting exactly 13 baskets out of 15 is whatever the probability or the Y value is for that one histogram bar. We don't want any of the others. That is when it's PDF. That's individual. That's just this bar here. Okay, that's no other bar. And here's the syntax or the spelling that you put in your calculator. First you have to put the total number of trials, comma, and then you put in the probability of success. By the way, that little comma button is just above the 7. A lot of people don't know where that is. Probability of success is 0.85, and just exactly which histogram bar do we want? The one with 13. So all you got to do is put that in there and hit enter, and boom, you got the same answer as using this little procedure. Okay. Now suppose we change our question around a little bit, and maybe we want, let's say scoring a basket. Same thing, only this time we want that he scores not exactly 13 out of 15, but say that he scores 13 or 14 or 15 out of the 15. What's that probability? Well, you could do it using this, and what you'd be changing is you'd have to work out this one, get that probability. Then you'd go back and change your 13 now to a 14, and change the 2 to a 1, work out that probability, and then you change this to a 15, 15 and 0, and you'd work out that probability and add the 3 together. But that's kind of tedious and time consuming. And you could use probability or the binomial probability density function and use this and go 13 and then do it again for 14, then do it again for 15 and add those 3 together. But there is a faster way. What it is, we use this cumulative. Okay, and that's just, you'll find that in the same location on your calculator. Basically the same syntax, and there's one little important difference. This one is now cumulative. And so in order to do the following, what we really are after is we want, and I'm just guessing that it might look something like this. This might be what our histogram bars look like, but we want this one plus this one plus this one. Those 3 probabilities. Cumulative works from the left. It adds probabilities, the histogram bars, from the left to wherever you end up stopping. So for example, if I put in a 5 here, it's going to add the probability of getting none, 1, 2, 3, 4, and 5 successes. That's what I'm going to get, cumulative probabilities from the left up to and including 5. So what we do is we use the complement. We do the following to answer this question. Now let me just get rid of this so it doesn't look like this is part of my answer. Okay, but this part is, and I do one little change. I go, well, let's go 1 minus. Now 1 would be if I added all of these, I guess there's actually 16 histogram bars. If I added all 16 up, I would get 1, 100%. That covers every possible probability. I'm going to take away everything up to and including the 12th bar. Now what that means is, here's number 12 here. Okay, let's say it looks something like that. Whoops, I guess these are actually touching. Okay, I'm taking all these ones here and I'm erasing on. I'm getting rid of them. I'm going 1 minus those. And what's left? The 3 that I want. So in case you work that out, I did. And I got a probability of 0.604. So it's very probable, very likely that this guy, because he's got a pretty good chance of scoring a basket at each given trial, the probability of getting either 13 or 14 or 15 out of 15 is about 60 and a bit %. Not too bad. Anyway, that's our look at the binomial distribution and some speedier ways to start calculating out probabilities of a lot of very lengthy experiments. Very interesting, very fun stuff. We'll catch you later.